All right, welcome to Chapter 11, Part 2. In this section, we're going to talk about integrated rate laws and half-lives. In the last portion, we were looking at differential rate laws, which takes a look at initial rates, but based on certain concentrations. But we know over time, as a reaction moves forward, that those concentrations are going to change. And the differential rate laws that we looked at in the previous video doesn't predict what happens at some later time. An integrated rate law is going to talk about concentration as a function of time. So it will explicitly tell us how concentration is going to change. And this is what is known as an integrated rate law. Now, in this section, there's a bunch of math connections and mathematical proofs. You don't have to know how to do that for this class, but if you are really interested in some of that calculus, this is a great chapter for you to do a little behind the scenes reading. We're going to jump straight to the integrated rate laws and look at what they mean and how we can use them and how we can determine reaction order based on graphing. So we're going to start off looking at the zero order rate law. A zero order rate, we know differential would look like this, right? It's going to be rate equals the rate constant times the concentration raised to the zero order, right? That's telling us that if we change the concentration, nothing happens to the rate. So it's not really surprising that this is a fairly straightforward integrated rate law. Something that you might notice here, we're looking at concentration of A at time t, so whatever time in the future we're interested in, equals the initial concentration, so that's concentration at time 0, minus kt. So minus the rate constant times time. And it looks very similar to the equation for a line, kind of a y equals mx plus b. And so what we find is that with zero order rate reactions, as the reaction moves forward, so as time marches forward, the amount of our reagent, in this case, whatever this one was looking at, decomp of N2O, that as time moves forward, the concentration of N2O decreases linearly, right? So something to take away from is if you are plotting concentration versus time for a zero order reaction, that is going to give you a linear plot, right? Keep that in mind. We're going to see differences when we look at other reaction orders. When we go to, and here is that derivation of the zero order. It's so much fun calculus. And let's continue. A first order reaction, which we tend to use the most, is going to look a little bit different. And there's two ways that we can write it. We know that the rate for a first order is going to have 1 as the exponent. So the rate is affected by the changing concentration. So our formula for a line looks a little bit different. It's based on natural log. It's based on this sort of like logarithmic function. This is useful depending on what you're solving for, but it can be more helpful to also know that the concentration at time t is equal to the initial concentration times E raised to the negative kt. Just depending on what it is you're solving for. If you're solving for a rate constant, this guy might be better for you. If you're trying to solve for one of the initial or final concentrations, this form is going to be a little bit easier. Something to note here is what happens when we plot. Well, if we plot concentration versus time for a first order reaction, it's not going to be linear because as we have less reagent, the rate is going to get slower, and so the disappearance is also going to get slower, and it's going to look more curved. However, if we plot the natural log of concentration versus time, we do get a linear plot. So you're going to be able to take data and graph it, and based on where you have a linear plot, you're going to be able to tell what reaction order is appropriate, right? 0 order here, first order here. Okay, so let's solve a problem using the first order integrated rate law. The problem that we're going to use is not the one in the slides. It's from your book, and it also has a typo in it on your notes. So let's fix that before we move on. We're going to make this match the book. We want to know the concentration after 2 hours, not 2 days. It's going to make a big difference when we go to check our work. All right, so let's get started. What do we know? We're given the rate constant, so we know that K is 2.95 times 10 to the negative 3 inverse minutes. We know that our initial concentration, so A sub 0, is 7.5 millimolar. We want to know A at time T, right? What will the concentration be after 2 hours? So T is 2 hours. Now, hopefully something that you notice here is that K is in inverse minutes and time is in hours. So we do need to fix that. So let's go ahead and convert that to minutes real quick. We know that in 1 hour there are 60 minutes. So our time is really 120 minutes. Since we are trying to solve for A sub T, let's use this version here. We're going to, since that's already isolated by itself, that seems reasonable. A sub 0 is 7.5 millimolar. And we're not told what kind of molarity we're looking for, so fine, we'll find our answer in millimolar. This is going to be multiplied by E, right? You can find that on your calculator, raised to the negative 2.95 times 10 to the negative 3rd inverse minutes times 120 minutes. So minutes will cancel out. We'll be left with just millimolar. Once we plug that into our calculator, we find that the amount that is going to be left, the concentration that's going to be left after 2 hours, will be 5.3 millimolar. Right, and so that is one way we can use our integrated rate laws to solve problems. We're going to keep going now and take a look at a second order integrated rate law. Second order integrated rate laws, right, as the concentration changes, that affects the rate exponentially. And so the rate law looks different, the differential rate law looks different, and so the integrated rate law also looks different. You'll notice that instead of concentration or natural log of concentration, we're dealing with 1 over concentration. So when we go to graphing this, it's really interesting. We'll look at what they did over here on the slides. The way that you can use data and integrated rate laws to determine reaction orders is by simply graphing. So this experiment of NO2 in the atmosphere breaking down to NO and O2 was studied, and the concentration of NO2 was measured at 5-second intervals. So then this data is graphed, and first they're looking at NO2, just concentration versus time, definitely not linear. Then we look at natural log of the concentration versus time, not linear. But then when we look at 1 over the concentration versus time, it is linear. Now it's increasing because we're looking at a fraction, but it is linear. And so this is characteristic of a second order reaction. So you can tell pretty easily if you do one of these kind of plots, right? Time versus concentration, and you plot concentration, natural log of concentration 1 over concentration. If any of those are linear, you'll be able to tell if it's a 0, first, or second order reaction. Now, if none of those are linear, then it's more complicated and it has a different reaction order. And that's okay. You're not going to be responsible for that. Another time and quantity that's really interesting when studying kinetics and rates is half-life. So as we are looking at the depletion of a starting material, the half-life is going to be the time it takes to fall to 1/2 the original value. So we're going to come back to these equations in just a second. It's easy to see here. So this is a first order reaction. And we see I want to explain something here. Normally when we talk about concentration, we're talking about molarity, and we see the brackets. But if we're looking at a gas, sometimes concentration instead is given to you in partial pressures. You know that from your gas law chapter, pressure is directly related to amount. So it works in the same way. So you could do concentration here in molarity or pressure. So we're starting though with this initial concentration of 1 atmosphere. When we have used up half of this ozone, when we get to 0.5, right, that is our half-life. And in this case, the degradation of ozone in light falls by half every 19 hours. That's the half-life, T 1/2. So then we would expect after another 19 hours for it to drop to 0.25, and that's what you see. And then after another 19 hours, we would expect it to hit about 0.125, right? So it's going to go down by half every 19 hours. This is the equation for a first order reaction. So it would be different for different reaction orders, but this is the one you need for first order reactions, which is where the focus is going to be. Now, something to note here. T 1/2 equals 0.693 K. This is just simplifying the natural log of 2 over K. You could plug K in either way and you'll get the same answer. So if we look at a problem where we're solving for half-life, this is the same reaction we looked at over here. This is the amount of ozone that depletes in light, right? Or the rate of destruction of ozone. But we're going to solve for the half-life if it is dark, right? So we're looking at decomposition of ozone in the dark. Things like light, temperature, concentration, these all affect rates. So we're going to take this equation. There's only 2 variables and we know one of them, right? So we know K, and we're just going to plug and chug to solve this problem. All right, so T 1/2 equals 0.693 divided by 3 times 10 to the negative 26 inverse seconds, right? So 1 over inverse seconds will give us seconds. And we find that the half-life is 2 times 10 to the 25th seconds. Now that's such a big number that it's kind of hard to kind of wrap your head around. If you convert that to hours, it's 5.5 times 10 to the 21 hours. That is a huge amount of time for it to decrease by half, especially since if you just add light, that half-life is only 19 hours. So you can really see how important certain wavelengths of light are in destroying the ozone. In the dark, it takes a lot longer.